differential properties of the forward operator. And we saw that we can solve any linear inversely posed problem by means of, for example, Tikhonov regularization. And today I'd like to speak about a specific inverse problem that you already heard about in the last week and that you already heard about yesterday in Peter Kuchman's talk, which is electrical impedance tomography. So I guess most of you have heard about electrical impedance tomography, but let me nevertheless start with a short introduction on that. And before I forget to mention it, let me make some shameless advertisement wallpaper. So what I'm telling about today is basically in the paper recent progress on the factorization method for EIT, and you can download this from my webpage. So basically what I'm showing you today is some kind of a light version of this paper. So what is EIT and why are mathematicians so very keen on studying EIT? Well, I think we saw these pictures already yesterday in my talk. The general idea of EIT is that you attach electrodes to the boundary of a patient, and then using these electrodes, you apply voltages to the electrodes, so currents will flow through the body, and then you measure the currents that flow and the voltages that you need to make these currents flow. And from this data, you try to find out how the inside of the patient looks like. And yesterday in the talk of Peter Kuchman, we heard that EIT is a low-resolution technique. And of course, this makes it interesting for mathematicians to study how can we improve the resolution. But I'd like to show you a movie how bad the resolution really is. And calling it a low-resolution tomography technique is quite flattering for EIT already. So let me show you how bad things really are. What you see here is a movie of EIT reconstructions from a real measurement at myself. So I had some electrodes attached to my body, and what you can see here is these two blobs getting larger and smaller are my lungs. So this uses the measurements of EIT measurements around my chest, and then while I'm breathing, we are making images all the time. So what you can see from these pictures is that EIT is really an extremely low resolution technique. If we would be able to get a resolution in the, let's say, 1 centimeter regime, we would be extremely happy. What we have nowadays is more like a 5 centimeter or a 10 centimeter resolution if you think of breast and or chest or thorax imaging. But still, these images are great for the doctors. Because if you have a patient connected to an artificial breathing machine, then these images are everything that the doctor has. So before he has these images, he just can look at the patient and can take the body weight of the patient to try to adjust the pressure that he takes for the artificial breathing machine. And if he has images like that, then he can see whether both lungs are filled with air or not. And actually that's what doctors would like to see. So if we can tell the doctors in a reliable way that both halves of the lung are filled with air or not, the doctors would be extremely happy, and this would really be a great machine to use that could save people's lives. So right now, persons are not really hoping to get EIT to a, let's say, millimeter resolution technique, at least not without using the hybrid imaging ideas that you will hear about in the other lectures. But what people are really hoping for is to use EIT as a low resolution technique, and the big goal that we have is to make EIT a reliable low resolution technique, and there's really a heap of applications for low resolution techniques as long as we can continuously monitor the patient in a harmless way and get low resolution images. This would still be really, really great in practice. Now, the mathematical model behind EIT, or what's really the inverse problem behind EIT, is that the electrical potential inside the patient solves such an elliptic partial differential equation, divergence of conductivity times the gradient of u is equal to 0. So the partial differential equation lives in the domain that is the patient. Often we assume that we have a two-dimensional cut through the patient, which is not really a justified model assumption because currents flow in 3 dimensions, but often this works fine in practice. And the coefficient in this PDE is the conductivity of the patient, so the coefficient is the thing that we are interested in. the solution of the PDE is the electric potential that will be there inside the patient when we apply some voltages on the boundary or we apply some currents along the boundary. And at least in a very idealistic model that is that mathematicians like to use and that usually is helpful to study first before you go to real electrode measurements, is that the applied electric currents on the patient can be modeled by the Neumann boundary data for this PDE. So the Neumann boundary data will tell you what currents you applied, and the measured voltages on the electrodes are given by the Dirichlet boundary data. So that's the idealistic model assumptions of having an infinite number of electrodes everywhere along the patient so that you can really apply continuous function on the boundary that are your applied currents or that are your measured voltages. And with that idealistic assumption, the mathematics behind EIT, behind the forward problem of EIT, are very, very well understood. So this is standard textbook PDE knowledge. The natural space for the coefficient of such an elliptic PDE is the space of essentially bounded functions, Lebesgue functions. So we take the space of L-infinity functions for the coefficient sigma. The subindex plus means that these functions should be positive in the L-infinity sense, so there should be a small constant. The essential infimum of these functions should be positive. And then the natural space to look for a solution is the Sobolev space H1. And as you can obviously see, constant functions will always solve this elliptic equation. So there's a certain non-uniqueness in this equation that corresponds to fixing the ground level for your electric potential. So the natural space to look for a solution is the space H1 together with some kind of condition that cancels out constant functions. And the natural condition, at least mathematically the natural condition, is to assume that your voltages, that your electric potential has a zero mean value, integral mean value on the boundary. So this fixes the ground level and is something that makes sense mathematically. And so this space H1 diamond is usually the natural space to look for a solution of this equation. And then the natural spaces to have the Neumann boundary values and the Dirichlet boundary values for such an elliptic PDE would be H minus 1/2 for the Neumann boundary values and H plus 1/2 for the Dirichlet boundary values. But things are even simpler if you work with L2 for the Neumann boundary values. It's a subset of H minus 1/2. So you can say I apply a Neumann boundary value that comes from L2. That makes sense for an elliptic PDE. And then I have Dirichlet values of the solution of the PDE that are naturally H1/2 functions, but H1/2 is also a subset of L2. So if you look at the function that takes a Neumann boundary value for this elliptic PDE to the solution evaluated on the boundary, then this is an operator going from L2 on the boundary to L2 on the boundary. And the standard textbook analysis tells you that this elliptic PDE always has a unique solution, and this is just a consequence of the Lax-Milgrom theorem. So you write this equation in the variational form, and then you have the symmetric coercive and continuous bilinear form on the left-hand side, and continuous linear form on the right-hand side, and Lax-Milgrom tells you that you have a unique solution for this equation. So what we can introduce is what are our measurements in EIT? Well, first of all, the engineers usually think of the measurements as just a big set of data. So they apply the voltages on the electrodes, they measure the currents or vice versa, and so they make a big table, what voltages did they apply and what currents did they measure. And they think of this as like a big table of measurements. Now mathematically it makes sense to give this big table of measurements a certain structure. So because we could think of this as applying a Neumann boundary data, we start with the Neumann boundary data for the PDE, solve it, evaluate the solution at the boundary. So this would give us a mapping between the Neumann boundary data that we applied and the Dirichlet data that we measured. And in fact, it turns out that we can make really, really fancy, nice stuff mathematically if we interpret our measurements in terms of this Neumann to Dirichlet operator. And also this is a nice way of really describing my idealistic set of measurements. So if we think of what are the most measurements I can take on a human body, the most kind of measurements I would have if I attach an infinite number of arbitrarily small electrodes, then I apply all kind of possible boundary currents to these electrodes. So all L2 functions that are there, I can apply to the boundary of the patient. And for all these L2 functions, I can measure the reaction of the patient, which means the voltages that will be there on the electrode. So this will give me then this Neumann to Dirichlet operator. And actually, of course, you could also make it the other way around. And on first glance, it seems more natural, because usually I would think of the causality in the sense that I apply a voltage and then I measure the resulting current. But many people like to use the Neumann to Dirichlet operator instead of the Dirichlet to Neumann operator. So we like to think of it as a current to voltage map and not as a voltage to current map. And the reasons are that in medicine, at least in Germany, there is a legal bound on the amount of currents that you can drive through a patient. So it's really the currents that you have to control in medicine and not the voltages. Of course, this would be equivalent, but the laws are that you have to control the currents. So that's why people in medicine like to think of it as a current to voltage map. And at least personally, I like to think of it as a current to voltage map, because then I can interpret this thing as an operator going from L2 to L2. And for example, if we think of measurements just on part of the boundary, it's no problem in going from L2 on all of the boundary to L2 on part of the boundary. And if you're doing these things with H1 half and H minus 1 half, you get all these nasty boundary effects that are mathematically interesting, but don't have any practical consequences. So if you think of it as a Neumann to Dirichlet map, then you just have L2 spaces on the boundary, and things just simplify quite a lot. And also this operator then has a very nice structure, because it's easily seen that this is a self-adjoint operator that comes from the fact that in the Lax-Milgram theory, the bilinear form is symmetric, so the equation is symmetric, which makes this Neumann to Dirichlet operator self-adjoint, and it's also a compact operator, because we have this L2 mapping from L2 to H1 minus to H up to the minus 1 half, or from H1 half to L2, which is compact. So it's the Neumann to Dirichlet operator, and then the H minus half spaces, which be continuous, and together with this compact inclusion, this is then a compact operator. So this Neumann to Dirichlet operator as a mapping from L2 to L2 is a very natural and nice thing to have in mathematics. Well, and then, of course, the forward and the inverse problem of electrical impedance tomography is, if we know the patient, if we know the conductivity, can we predict our measurements? Can we calculate our Neumann-Dirichlet operator? And this is easy, because it just means solving PDEs. So if we know the conductivity coefficient, we can, for every applied Neumann boundary data, solve the elliptic PDE, evaluate the solution of the boundary. This gives us the Dirichlet boundary data. And if we do this for all Neumann boundary data, some discretization of that, we get the Neumann-Dirichlet operator. Now, the inverse problem of EIT is, of course, much more complicated. If we know this Neumann-Dirichlet operator, if we know the boundary values of the solution of an equation, can we know the equation? Can we know the coefficient inside the equation? And of course, one of the big problems there is whether this is possible. Does there exist such an inverse operator from the Neumann to Dirichlet operator to the conductivity? And this is one of the maybe the most famous theoretical inverse problem, the so-called Calderon problem, that has really been great progress in the last 30 years, but which is still not solved completely. And I'm completely not talking about this Calderon problem in my talk. So let me just mention that at least for piecewise analytic conductivities, the uniqueness holds true. So if you believe that a person inside is piecewise analytic, which seems to make sense, then you can believe that EIT would really work. So what I like to speak about is how can we reconstruct the conductivity inside the patient from our measurements, and how can we do this in a good way? So what can we say mathematically about algorithms that give us the conductivity or some properties of the conductivities from our measurements? Now, there is a general theory on nonlinear inverse problems. So first of all, this is a nonlinear inverse problem, where Neumann-Dirichlet operator depends nonlinearly on the conductivity coefficient, because the solutions of the PDE depend nonlinearly on the coefficient of the PDE. So this is a nonlinear inverse problem. It can be shown to be ill-posed. So you can, it depends a little bit on how you define ill-postedness for nonlinear problems, but in all natural senses, this is really an ill-posed problem. And there is a theory you can construct something like Newton-type methods for nonlinear inverse problems, and there's a general theory about that when these methods do converge. But the bad news is that this general theory needs some assumption. And there are two kinds of assumptions that you need for convergence for nonlinear inverse problems. One is a condition on the nonlinearity, the so-called tangential cone condition or Scherzer condition. And this condition is not known to hold for EIT. So we don't have any counterexamples, but we don't have any proof that this condition holds. So we don't have a proof, so we don't know whether EIT, which is really a very simple mathematical problem, you can easily write it down, it's why mathematicians really love to study this inverse problem. Even for this very, very simple problem of the easiest elliptic PDE with a single coefficient inside, we don't know whether our nonlinear inverse problem solver holds, so we don't even have local convergence result for that. There is another condition that also ensures convergence, and these are so-called source conditions. So we assume that your true solution lies inside some spaces that have something to do with your forward operator. And under these source conditions, you also get convergence, but no one knows what these source conditions mean for EIT. So if your true solution fulfills a condition where you don't know what it means, if your true patient fulfills a condition where you don't know what this condition means for the patient, then we would have local convergence of standard methods, or if there's an assumption true for the general problem of EIT where we don't know whether this assumption holds true. So this is really bad news. Mathematically, we cannot really say much about convergence for EIT. But if you look at EIT as a general nonlinear inverse problem. And so maybe the best thing that's out there in terms of convergence is the D-bar method that Knudsen will talk about in his lectures, where he will use, at least under some specific assumptions, and in 2D and also in 3D, as he just told me yesterday, they have some convergent implementations for this D-bar methods where they really can show convergence, and mainly the assumptions are, you can correct me if I'm wrong, that they have access to measurements on all of the boundary, and that the coefficient is a C2 coefficient. So that's what you need to get some specifically designed for EIT reconstruction formulas. Now, what I would like to talk about in this lecture and the lecture tomorrow is not really the problem how to get the conductivity coefficient out from the measurements, but I would like to concentrate on a more specific problem that turns out to be simpler in the mathematical sense, but still holds a lot of relevant information. So because what we are using EIT in practice is, for example, to monitor the lung shape. So we want to know which parts of the lung take part in the breathing process. So we have, let's say, two measurements, one at the exhale state, where there's no air in the lung. Then I start breathing, and then you take another measurement, and you want to find out where did the conductivity change, which part of the lung is now filled with air, so that the conductivity is very different from the fact when it was not filled with air. So that we are often you have this kind of ideas behind EIT. You want to find the part of the body where the conductivity differs from some, let's say, reference value or some background value. For example, if you look for cancer detection, then you know some kind of normal background value for, let's say, the human breast, for example, in mammography, and you know that the cancer cells and breast tissue have some very different conductivity, so you try to find out where is the conductivity very different from a reference value. So often you have something like two measurements, let's say lambda for one conductivity sigma, you have lambda for conductivity sigma naught, think of the exhale state, for example, and you want to know where did sigma change from sigma naught. So what you're trying to find out is the support of the difference of your two conductivities. And if you can get this from the measurements, then most of the many medical doctors, many applications would already be happy. And then the talk today and the talk tomorrow, I will concentrate on this inclusion or anomaly or shape detection problem. How can we get the support of a conductivity change? How can we find the location of a conductivity change from our measurements? And what I will do today is show you that there is really, let's say, explicit solution formula for this kind of problem. There is an explicit formula that tells us where does the conductivity change by looking at the measurements. And this explicit formula is known in the literature as the factorization method. It comes from Andreas Kirsch from the University of Karlsruhe from inverse scattering problems, and then by Martin Hanke, who's my PhD advisor, and Martin Brühl, which is a PhD student of Martin Hanke, they extended this original factorization method of Andreas Kirsch to electrical impedance tomography in 1999. And since then, there's been a lot of work on extending this factorization method also to other problems, to more realistic electrode measurements, relax the assumptions, simplify the proof, and all this stuff. And what I'm showing you today is on a recent review article on this factorization method, where I try to summarize the proofs and how we know now that the proofs can be simplified and write up the proofs from a modern perspective. And well, this factorization method gives us an explicit characterization of where the conductivity did change. And this explicit characterization I put below here. So the factorization method will tell us that a point belongs to the area where the conductivity did change. We can find out whether a point belongs to this area by constructing a special function that belongs to this point. This will be a function that has a singularity at this point, and at least for easy geometries, we can really write down this function, otherwise we can calculate it. Then we take this function, take the boundary values of this function, and we check whether this function lies in the range of some operator that we can construct from our measurements. So what we need is the measurements for our one conductivity, let's say the inhaled state, our measurements for the other conductivity, some reference conductivity, let's say the exhaled state. Then we take the difference of these two Neumann-Dirichlet operators. Then we take the square root of this difference operator in the operator sense, and we will see where this comes from in the proofs. And then this is an operator again, and then we look at the range of this operator, and we check whether a certain function belongs to the range or not. So this is some crazy kind of formula to check, but it's great because it's really, really explicit. So if we have this kind of formula, then this immediately tells us that we can get the support of the conductivity change from our measurements, because we have an explicit formula telling us for every point, did the conductivity change in this point, or did it not change in this point? And you also see that it's very important for these kinds of formulas to really look at your data in the sense of Neumann-Dirichlet operators and not just in the sense of having a long set of measurements, because we are really using the operator structure here. We are using the fact that we can take square roots of positive definite compact operators, and we are using the fact that operators have ranges where we can test whether something belongs to that or not. So this whole idea is really, really based on everything here is really based on the fact that we are looking at our data in the Neumann-Dirichlet operator sense. So what I'd like to show you here in this lecture is where this formula comes from and why it holds true. And the outline of the proof is, well, of course, first of all, we have to say what these special functions are. I told you that we can construct functions for given a point. We construct a function with singularity in that point, but I will have to show you what these functions really are. And then we will introduce some very useful auxiliary operator that I like to call a virtual measurement operator. And we will see that this operator tells us, or the range of this auxiliary measurement operator tells us where our conductivity changed. So the range of this operator will already tell us if whether in a point the conductivity changed or not. And after that, we will show that the range of this auxiliary operator is really something that we can calculate from our measurements. If the range of this auxiliary operator is the same as the range of the square root of the difference of the operators that we measured.
May I ask you?
Yes,
those you look at Neumann-Dirichlet, so these are compact operators.
Yes.
So their ranges are not close.
No.
So,
and otherwise, this would be a strange thing here, because otherwise the range would just contain everything.
Is there any way to find whether a given vector belongs to a non-closed subspace?
Yeah, I mean that's a perfect question, and actually this question will be the motivation why I have another talk tomorrow. So let us try to concentrate today, or at least until the last slide, let us try to concentrate on proving this thing, that we can construct the anomaly from the range, and then we will go to this excellent question on whether this is useful numerically or not. It is at least useful theoretically, and we will see in the lecture tomorrow what we can do numerically on that. And So to show you why this is, where this really a little bit strange, maybe a little bit weird range condition comes from, I'd like to really show you the proofs. And I'd like to show you the proofs for a simple test case, which just simplifies the proof, and if you understand the proof for the simple test case, then everything else is just a little bit more technical work. The simple test case will be that the reference conductivity, the exhale state, will just be a conductivity of 1 everywhere. And in the case where we have an inclusion and normally a conductivity change, we will assume that the conductivity is 1 everywhere, but inside some part of the domain, the conductivity will be 2. So sigma naught omega our domain, sigma naught will just be 1 everywhere. And in the inhale state, let's say my 2 lungs have a conductivity of 2, which is obviously nonsense because they have less conductivity if I inhale it. Just stay with this example, and these domains here, this is called D. So I try to take the measurements for this conductivity, for this non-conductivity, and I try to find this D. And also we make the assumption that D doesn't have to be connected, but we will assume that the exterior of D is connected to the boundary. And we can relax all these assumptions. It doesn't have to be 1 and 2. We can make it for piecewise analytic functions, and for D's where the exterior is not connected, but things get a little bit more complicated there. So let's assume for this lecture that we have such a simple case, and we try to find out where this D is. Now, let's start with these special functions. So the special functions that we use to test whether a point belongs to D, to a place where the conductivity changed, are the so-called dipole functions. So we take our EIT equation with the conductivity being equal to 1, and divergence sigma gradient U is just Laplace of U. And then we solve this equation with 0 Neumann boundary values, but with a right-hand side that has a delta type singularity, or to be more precise, a derivative of a delta function. So delta Z should be the delta function in the point Z, and then we take the gradient, and D times the gradient, so this means we take the derivative of the delta function in the direction D. And D is any direction, and everything I show you here will work for any direction D. So this is something you can use numerically, or you can, if you're just interested in the math and the proofs, you can always fix D to be the unit vector, let's say in the x1 direction, and then what you have on the right-hand side is the delta function, and then the derivative of the partial derivative of the delta function with respect to your first coordinate vector. And you can think of this as an electric dipole source. So you may think that there's some person who has at some point in your body make sure that the current is going to this right direction. So he's applying some kind of a source term, and you can then, let's say, measure on the boundary what effect does this source term have on my measurements on the boundary. And you can calculate this function for a given domain. That's quite simple. You can also do some kind of adjoint tricks to, instead of calculating this function, you calculate some kind of reference solutions. And for easy geometries, you can even write down this solution. This is something like a fundamental solution for the EIT equation, and a derivative of a fundamental solution of this EIT equation. And for simple geometries, this is known, for example, for a 2-dimensional ball. I gave it to you down there. You can really write it down. So if we believe that we have these functions, and these functions somehow correspond to putting a source term in one point inside the boundary, then let's introduce the so-called virtual measurements. So the virtual measurements are something that is very, very similar to having a point source inside the body, but now we assume that we have a volume or an area source. So I termed this virtual measurements because I always thought sort of having some kind of small partner that sits inside the body of the patient in some part of it. Let's say this D. He sits in the part where the conductivity changed, and in this part he applies sources. He applies some kind of current or voltage sources for my equation. So we have this small partner sitting inside D. He's applying source terms here, and the outer boundary is insulated, but this will have, if he applies some sources here, this will have an effect on the electric voltages inside the patient, and I can measure this effect on the outside. So he applies a source here, and I measure the corresponding voltages here. And I put this down, the true definition in the variational sense. It's a very nice thing to put it down in this variational sense, because then it works also if this D somehow intersects the boundary here. But if D is really compactly contained in omega, so if D doesn't touch the boundary D omega, then this variational equation is just equivalent to Laplace D equals to divergence of F with zero Neumann boundary data. So we take again the Laplace equation, we give source for the term for the Laplace equation, but this time the source term is not just a dipole source in one point, not just the derivative of the delta function, but this time we take a function f that is an L2 function in this part D with n components, so that this divergence makes sense. So this time we do not apply just one source in one point, but we apply sources all over D. And then I could think of this experiment and ask myself, is it possible if I have this small partner sitting inside D and he applies all kinds of sources to D and I measure the resulting voltages all the time on the omega, is that enough information to find out where my small partner is? Can I find D from this experiment? And in fact I can. And the very nice thing is I can do that from the range of this measurements. So I don't really have to know what kind of sources he applied, my small partner. I only have to know what I can measure on the outside, and if I know everything that can be constructed in such a way, if I know every function that can appear as the boundary values of a source of a voltage corresponding to a source term in D, then the range of this virtual measurement operator contains all the information about where D is. And this is almost correct. So let's assume that D is just an open domain with no boundary smoothness assumptions. Then what we can find this way is the interior of D. We can distinguish the interior of D to the exterior of D. We cannot say anything about the boundary of D, but it's a set of zero measures, so usually we don't care about that. And how can we do that? Well, it's connected to this dipole function. And this dipole function lies in the range of our virtual measurement operators if and only if the location of the dipole lies inside D. And I gave you the proof in my lecture notes on my homepage. I gave you the proof for this. It's, let's say, one page of proof. It's not very complicated, but it's too long to really do this in the lecture, and it's a boring proof because it's just technically. So the proof of theorem 3.3 I'd like to refer you to the lecture notes and just gave you a hand-waving proof that contains all the ideas of how to do this proof really. So we have our dipole function that corresponds to the fact that someone put a source term in one point, a very singular source term, a derivative of delta function, distributional source term in one point. And if this one point lies inside D, this is Z, and if Z is inside D, then we can use, or we could be tempted to use this dipole source term as the F here. So if you think of, for example, that you have the dipole going into the x1 direction, then this would correspond to F being a vector with a delta function in the first component and zeros everywhere else, and with the F being a delta, this down, let's say F is the delta function in Z, and then zeros in the other components, and then the divergence of this thing would be derivative of the delta function with respect to the x1 coordinate. So if this guy here was in L2D, then we would have shown that if Z is in D, then we can use then the dipole function's boundary terms belong to the range of LD, because then we could choose the F to be this dipole singularity. And of course, this doesn't belong to L2D, but it doesn't really matter because we have some space around Z, so we can smooth this F to make it belong to D, and then with a smoothed version of this, we can say that it has the same effect. Doesn't matter whether my small partner applies a dipole singularity in the point Z, or if he applies some kind of smoothed version of this all around D, we will still get the same measurements on the boundary. So this means that Z is in D, a smoothed version of this thing shows that, how did we call it, phi Z is in the range of the virtual measurements. So with this argument we can show that if the dipole singularity is in D, we can also construct the same boundary values by using some kind of area source term here. Now let's assume that Z is not in D. So if that happens, and assume we could have the same effect, the dipole source in Z could have the same effect as some source term here on D, then this means that we will have the same solution, the same values, the same boundary values for the solution of the Laplace equation with the singularity in Z, and for a solution of the Laplace equation with the source term here in D. And then by unique continuation, these two solutions must be the same everywhere, outside D and outside Z. But this means we can, if the two solutions are everywhere the same, this means that we can follow the solution up to the point Z, but one of the solutions has a singularity in Z, a dipole singularity, and the other solution does not have a singularity in Z. So you cannot have two solutions that are the same until everywhere outside this point Z, but one solution has a singularity and the other doesn't. So what we use then is unique continuation to show that it's not possible that we have two solutions, one with the source term here, one with the source term here, that have the same boundary values. And this means we cannot have the same boundary values, so this means that phi Z cannot be the outcome of such a virtual measurement with a small partner sitting in D. So this virtual measurement operator is really a great thing, and it really comes from inverse scattering. If you're familiar with that, that's some kind of an analog to the Herklotz type operator. So in scattering, people usually think of the scattered wave going in to some kind of scattering object. So they send a wave, the wave goes to the object, and the object somehow reacts and sends the wave back to where you do the measurements. And this is the analogy to this virtual measurement operators. In EIT, you usually don't think of currents going to an object and then coming back, but still the math is still introducing these kind of objects are still very useful. So you could still think of somehow you send something in the domain, and the fact that you have something in there, and that you have this D there, will have some effect on your outer measurements, and this effect will act like a source term in D. And you can find out where the source is from looking at the range of your virtual measurement operators. Now, another nice thing about this virtual measurement operator is that it's adjoint. It's a really useful thing. So, if you're familiar with these things, then you can calculate the adjoint in your head. So going from a source term of an elliptic PDE to the Dirichlet boundary value, then the adjoint of this is going from the Dirichlet boundary, going from the source to the Dirichlet boundary value. The adjoint of this is going from the Neumann boundary value to the evaluation of the solution. And this is really true. The adjoint operator of this guy here is an operator that takes a Neumann boundary value and applied current on the boundary, and maps it to the solution of the homogeneous EIT equation evaluated on this part D. And this is very easy to prove. And the proof of theorem 3.4 is if you have some G belonging to the space of our currents, L2 on the omega, together with this diamond with normalization condition, and if we have some source term F in L2 on our inclusion D, then the scalar product in this space, L2dn, is just the integral over D. So the scalar product in L2dn is the integral over D. Look at L star G times F. This would be the scalar product between L star G and F, and we want to find out what L star G is. So we know by definition L star is defined as what happens if we write the L on the other side and the scalar product of the other space. So the other space is L2 d omega. So the other scalar product is the integral over the omega. G L F. So LF was defined as the solution of our homogeneous Laplace equation when we have F as a source term, and then evaluated on the boundary. So this is G times V evaluated on d omega. And now we use this function here. This function u0 is a solution of the Laplace equation with Neumann boundary values G. So if using Cauchy's formula or the variational formulation of the Laplace equation, this thing here is the same as the gradient of the solution u0 that has this Neumann boundary data together with any function that has this directly boundary values here. So let's take V here. And then we know how we defined V. We defined V as being the solution of this equation here. And if we use the variational formulation of the solution that we had on the slides, then it said that the gradient of V times any H1 functions should be the same as F times the gradient of the H1 function. So this is the same as gradient u0 times F on D. And this shows us that for any F, L star G and gradient u0 are the same. So this shows that L star G must be the gradient of u0 on the subdomain D, and that the adjoint of going from source to directly boundary values is going from Neumann boundary values to evaluations of the solutions. Now, this adjoint operator also appears in some very, very nice formula. Actually, I'd like to really stress out the formula that we have here, because a lot of our work nowadays is really based on this monotonicity principle. But if you think of current voltage measurements in the easiest case, let's say you have one piece of wire and you want to find out what is the resistivity or the conductivity of this piece of wire, then there is a very, very natural monotonicity condition there. So if you increase the conductivity of your wire, then you need, let's make this right, then you need less voltage to drive the same current through the wire. So that's a trivial monotonicity thing. More conductivity means you need less voltage to drive the same kind of currents. And this kind of monotonicity can be transported to, can be extended to multi-electrode measurements. So that's again a reason why it's a very good thing to think of your measurements as an operator, either in Neumann to directly or directly to Neumann, usually Neumann to directly. Because if you look at the Neumann to directly operators, these guys are compact self-adjoint operators. So we also have a half ordering on these compact self-adjoint operators, because they are also can be also be shown to be positive, but you don't care. So they are compact self-adjoint operators, and we have a half ordering on them, meaning that you say that one compact self-adjoint operator is larger than the other compact self-adjoint operator if the difference has only positive eigenvalues. And with this half ordering on the space of compact self-adjoint operators, we still have the same nice monotonicity properties, that if we increase our conductivity everywhere, then we need a smaller Neumann-Dirichlet, then we get a smaller Neumann-Dirichlet operator in the sense of positive definiteness. And this monotonicity is a consequence of this equation here. If you look at this, this is the scalar product of function g, the current g, together with the difference of two Neumann-Dirichlet operators. So this is the quadratic form for this difference of the conductivity operators lambda sigma 1 minus lambda sigma naught. And if sigma, let's say sigma naught, is always larger than sigma 1, then this integral here on the left-hand side will always be positive. And this means that this quadratic form from the difference of the Neumann-Dirichlet operators will always be a positive semi-definite quadratic form. So this means if your sigma naught is larger, pointwise almost everywhere, than sigma 1, your corresponding Neumann-Dirichlet operator lambda sigma 1 is larger than lambda sigma naught in the sense of positive definiteness, like difference has only positive eigenvalues, so quadratic forms are always positive. And this is an extremely useful identity, because if you now look at this, read at these integral expressions here, this gives you even more than just this monotonicity that we will heavily use in the next talk tomorrow, but it also gives you some kind of a connection between the difference of two Neumann-Dirichlet operators and the difference of the corresponding conductivities. And I mean, this is exactly what we are interested in EIT. We want to have a connection between what the conductivity does and what the Neumann-Dirichlet operator does. And this is I would say, the most explicit kind of connection that we have between the conductivity and the Neumann-Dirichlet operators. And since this is so very nice and so very important, I'd like to prove at least part of it. So, proof of 0135. Well, first of all, it's useful to note how these quadratic forms look like. So what's the quadratic form of the operator lambda 0? And I use the shortened notation that lambda 0 always means lambda for sigma naught. And if I write something like u0 or u1, then these are the solutions for sigma naught and sigma 1. So what is this quadratic form? Lambda 0 g takes g to the solution of the Laplace equation and then evaluates on the boundary. So this would be u not evaluated on the boundary d omega. And now this thing is, again, we can use the variational formulation for the u naught, and the variational formulation says that g times any boundary function, any boundary values of an h1 function is the same as the integral over sigma naught gradient u naught times this h1 function where we have the boundary values here. So this is the same as sigma naught gradient u naught times gradient u naught. But on the other hand, this g is also the Neumann boundary data for the function u1. That we solved the conductivity equation of conductivity sigma 1 with the same Neumann boundary data, then this g is also the Neumann boundary data for u1. So using the variational formulation for u1, this is also the same as sigma 1 gradient u1 times any function that has the same boundary values as this guy here, times the gradient of u naught. So these two guys must be the same, and essentially the proof is only using this together with the coercivity. So what we do is, we look at this expression here, sigma 1 gradient u1 minus u0 times gradient u1 minus u0. This is something nice because we know the sign. This is always a positive function. Sigma 1 is positive, and here we have 2 times the same thing. So what we have here is always non-negative. And then we can multiply it out, and if we multiply it out, we get terms like this. So they tell us something about the Neumann-Dirichlet operators. So let's do this. This is sigma 1 gradient u1 squared. Then we have 2 times sigma 1 gradient u1, u0. So let's write them both down. That would be sigma 1 gradient u1 times gradient u0. Then we also have sigma 1 gradient u0 gradient u1. And we have sigma 1 gradient u0 squared. Now, this guy here is the same as we have here. So this is the same as the integral over sigma naught gradient u0 squared. And also this guy here is the same. And I will use that this guy here is this quadratic form for lambda 0. So this is the same as the integral g lambda 0 g. And now this guy here, we can use exactly the same formula with lambda 1 instead of lambda 0. So with lambda 1 we would have sigma 1 u1 here, which is precisely this term. So this term here is g lambda 1 g. And if we now collect everything, we have that this thing here, which is non-negative, must be the same as g lambda 1 g minus g lambda 0 g. And then we have sigma naught and sigma 1 together with this gradient u0 squared. So this is the integral over sigma 1 minus sigma 0 gradient u0 squared. And this shows us already this first inequality, because this term is the same as this non-negative term. So this means that this expression here must be positive, and if this expression is positive, then this shows that lambda 1 minus lambda 0 is larger than this guy here times minus 1, so with sigma naught minus sigma 1 inside. So this shows the first inequality. And showing the second inequality is not exactly the same, but it's just as simple as that. You just start with a little bit more complicated expression. You start with something where you have where you take sigma naught here, and then you take something like sigma 1 over sigma naught here. So again, if you multiply it out, you get these kinds of terms. And if you do this in the correct way, then you also get the second inequality. So it's just as simple as this first inequality. The second one is similar. Okay, and why does this thing help us in detecting the anomaly, in detecting the inclusion? Well, this helps us because this gradient unit, so let's go back to our simple example where sigma naught is just 1 and sigma 1 is 1 and it's 2 in some inclusions d. Then this means that this integral here and this integral here will just be integrals over our inclusion d. So we have the integral over the inclusion d together with this gradient u0 squared. So what we have is the L2 norm of our solution on the inclusion. And that's exactly what the adjoint of the virtual measurement operator was. So this shows us that we can bound the quadratic form of the two Neumann-Dirichlet operators from above and from below also by the norm of the adjoint operators of our virtual measurement space. So what we can get from our measurements is the norm of the adjoint of our virtual measurement operators. And in fact, we can write this quadratic form in a slightly more complicated sense. This also shows that this quadratic form is positive. So this means that lambda naught minus lambda 1 is a positive operator. Positive operators have square roots. And then we can interpret this quadratic form as the norm of the square root operator times g. And so this tells us that we have the norm. We have an estimate on the norm of the square root operator or of the difference of the Neumann-Dirichlet operators that is connected with the norm of the adjoint of the virtual measurement operators. And why does that help us? Well, the reason is a very, very nice functional analytic relation between the norm of an adjoint operator and the range of the original operator. And again, this has some kind of a monotonicity structure. So if I have two operators, they don't have to be defined on the same space. And if I have these two operators and I have an estimate on the norm of their adjoints, and one operator, one adjoint is always smaller than constant times the second operator, then this means that the range of the first operator must lie inside the range of the second operator. So if I have a norm estimate on the adjoint of an operator, I know something about the range of the original operator. And again, you can find the proof in my lecture notes. Again, this is a proof that's just, I don't know, half a page. It's really, really simple to show. It's essentially using Rees' theorem and nothing else. So again, this is something that can be shown in a very simple way. And it's very, very nice for us because we have a connection between the norm of what we can measure on Neumann-Dirichlet operators and the norm of the adjoint operators. And so this shows us that the norm of our square root of the difference of our measurements can be estimated from above and from below by the adjoint of the virtual measurement operators. So this shows the range of the difference of our measurements in the square root, that this range must lie inside and must be less and must be more than the range of our virtual measurement operators. And so this shows that the range of what we measure, the difference and square root, is the same as the range of our virtual measurement operators. And that already completes the proof for the factorization method, because we have seen that the range of this virtual measurement operator tells us where the inclusion is, and the range of this virtual measurement operator is the same as the range of something that we can calculate from the measurements. So this shows us where the inclusion is by looking at the range of something that we can calculate from our measurements. So what we have shown now is really an explicit, if you like to call it this way, we have an explicit formula of how to calculate this, the area where conductivity change from the change of the ERT measurements. And that's first of all, that's something really great. Let's start with the second point, because it shows us something about uniqueness. It shows us, because we have an explicit formula, it shows us that the part where the conductivity change is uniquely determined by the measurements. So this is first of all, so you can use this factorization method as a theoretical proof of proving uniqueness of the shape from the measurements. So this is first of all a great thing. Then let me maybe go to the third point. I only showed you the proofs for the very simple case that the conductivity is 1 everywhere, and then we have some part where it's 2. And if this is not the case, you can still do most of the proof. So it really extends to piecewise analytic conductivities. Everything we need is unique continuation in some part. So that's something that we need. We have that for piecewise analytic conductivities. And what we also need is that the inclusion has either a higher or a lower conductivity than the background. But essentially, if we have this, then you can extend all the proofs. And also you can extend all the proofs to partial boundary data. This is usually a big problem in the Calderon problem. And we don't have this problem at all. We don't have to care about the dimension of our object. We didn't use anything that depends on dimension. And we never use that we have our data on all of the boundary, because unique continuation also holds if we have data on an arbitrarily small part of the boundary. So there's a lot of extensions of this that we can, and in the paper we have these extensions really written down. Of the proofs, they're almost the same. Now I should explain where this name factorization method comes from, because there was no factorization in the proofs that we used. And in fact, this name factorization method comes from the original proofs of Andreas Kirsch and Martin Hanke and Martin Brühl. And I think it's always nice to, I like to point out that when I was in school and I learned math, and I thought math was all about calculations. And then when I was a student, I thought that math was all about mathematical proofs and this kind of logic thing. And now I believe that math is all about definitions. So if you have the right definitions and if you have the right concepts, then all proofs should become trivial and beautiful. So math is only finished when it became beautiful. And so it's usually a process. The first time that you have a proof for some kind of mathematical assertion, the proof is usually ugly and long, and there's a lot of unnecessary things in there, because that's how we make proofs. But if a proof gets older and older and the method gets worse, the proof simplifies more and more. And I think this factorization method proofs are much simpler if you write them in this monotonicity factorization free way, and then you can show the proofs in a lecture. At least most of the proofs are hand-waving parts of the proofs, while the original proofs would probably need the whole morning to show you because of some unnecessary complications in them. But I think it's still fair to keep this old name, factorization method, because that's really where the main ideas came from. And then let's come to your excellent question. Is this something that helps us numerically? Well, the practical answer is yes. We have used this on real data and we get something useful out of that. There are ways to find whether a function belongs to the range of an operator or not. And basically these methods are based on the fact that if you try to calculate a pre-image of your function, then if you do this in a regularized way, then your regularized solutions will tend to infinity if it was not possible to solve the original equation, but they will not tend to infinity if it is possible to solve your original equation. So there is a numerical implementation that basically calculates something and checks whether the something is infinite or not. And of course, in practice, it's never infinite, but you have some discretized version, and if you just make a plot of it, and when it's large, it seems to be infinite, and if it's not very large, then it seems not to be infinite. So from looking at these pictures, you can get some information in practice. But we don't have any mathematical rigorous proof that these numerical implementations really work. So we don't have any convergence proof in the strict sense that if we have a sequence of better and better measurements of our Neumann-Dirichlet operator, let's say more and more electrodes, more and more accurate measurements, do we have some kind of implementation that where what comes out, our reconstructions converge against the right reconstruction if delta goes to zero and we measure more and more accurately. We really have to say we don't have this for the factorization method, and the reason is that this range condition is just something that's numerically very, very hard to handle. But we now have another method which is very, very closely connected to this factorization method that can be stably implemented. And we will see more about this in the next lecture tomorrow. So, thank you for listening.
What about the values of the jumps?
Pardon?
What about the values of the jumps?
Well,
is that quantifiable?
So theoretically, you don't need any value of the jump. So you can have an inclusion. This is your reference conductivity. And this is the inclusion, and you still find the support of the inclusion.
Sure. So there could be times when to quantify your object, you need to know the jump.
Okay. I know what you mean now. So if you count the object, then it's, and if it's, for example, piecewise constant, then it's a simple thing to find the value of your jump, essentially by using this monotonicity. So if you know that you have an object here, and you don't know the value of the conductivity in here, you can just start with the reference value, you start raising it, and then by this monotonicity principle, you can find out whether your value here is too large or not. So this is like a one-dimensional inverse problems where you also have monotonicity, so you can make something like interval halving in order to find this level here.
So connected with the data basically, which you have.
Yeah.
With respect to that you know the support, only thing remaining is the piecewise constant.
Yeah.
And
then it's a one-dimensional problem which is already simpler, and you also have monotonicity which makes it much simpler. So please feel free to ask any other questions in the big audience or privately, whatever you like. Thank you.